Welcome to ARM Presents Fireside Chats, panel discussions looking at the business potential of technology. In today's episode, we're exploring how TinyML enables machine learning applications on resource-constrained microcontrollers. It breaks fresh ground on cost, power consumption, and ubiquitousness of smart systems. This fireside chat will discuss how TinyML will democratize and proliferate exponentially into a market that encompasses billions of consumer and industrial systems. The moderator is Xiao from ARM.
Thank you very much for joining this Fireside chat today. My name is Xiao. I'm from ARM Machine Learning Ecosystem team. Join me today are Steve Roddy. Steve is the VP of Product Marketing in ARM Machine Learning Group. And Zach Shelby. Zach is the co-founder and CEO of Edge Impulse. Steve, do you want to briefly introduce yourself?
Thank you, Wei. Good to be here today. Yes, I run the product management team for ARM for both hardware and software for machine learning. So we're heavily involved in enabling deployment of machine learning on devices big and small, and particularly the TinyML, the small edge area, is an area of really explosive growth. So it's good to be here to kind of share observations and sort of discuss the trends with Zach, one of the practitioners in this area.
Thank you, Steve. Zach is an entrepreneur, angel investor, and a technologist in the embedded space with a passion for TinyML. Zach, I'm going to hand over to you.
Thank you, Wei. Great to be here. Yes, I come from a fascination with how we can enable a lot of developers and engineers to bring new technologies into the embedded space. And for me, TinyML just has, unlimited possibilities. So we founded a company called Edge Impulse to help developers and engineers access machine learning on these embedded target devices. So ARM Cortex-M, ARM Cortex-A. How can we make that an easy process from data set collection to algorithm training, testing, and then deployment?
TinyML refers to the machine learning technologies on the tiniest microcontrollers, usually using millivolts range of power consumption. There have been a lot of talks around the TinyML for a while, and we began to see accelerated momentum in the past 2 years. So why is the surging interest in TinyML now? Why do we need to push machine learning to low-power embedded devices? Steve, I would love to hear your thoughts on this.
Sure. It's a very fascinating trend because, as you note, a lot more machine learning implementations have been deployed, prototyped, shown at trade shows, etc., over the last couple of years, really all on existing hardware. Well, there's a whole train of improved machine learning capabilities coming. ARM in particular has released several new NPU processors and M-class cores over the last year that we might touch on later in this hour. But most of the action today is on existing pre-deployed devices, making those sensors that people have deployed in IoT scenarios smarter, respond better, cut down on the amount of bandwidth that systems need. I think that's really been the trigger. When people a couple of years ago, 3 years ago, started thinking about the Internet of Things, started putting wireless sensors in factories, in industrial buildings, hotels, what have you, they quickly realized, wow, I'm sending a lot of data back and forth, and all of a sudden machine learning makes it possible to do a lot more analysis kind of on the edge. It makes those systems more powerful, makes them last longer on batteries, and people are just really starting to figure out how to make it happen. And so making it easier to deploy and easier for people to actually embed machine learning into their applications is really a key. And I think that's where a company like Edge Impulse really can move the needle on how these things are deployed in the marketplace.
Yeah, and Steve, you said it exactly right when you talk about the power consumption and the bandwidth requirements. We're seeing huge impacts from TinyML being able to just massively reduce the amount of data that has to be transmitted to the cloud. And that, of course, costs, right? It costs energy. but it also costs bandwidth, infrastructure, and the cloud is not free, right? We're realizing that pushing all this data to the cloud costs. And at the same time, right, we've seen a massive increase in the compute power available to microcontrollers over the past 3 years in particular, right? We've really started to see more and more powerful, right? These new generations of Cortex-M hitting the market, and they're not being used for much, right? If you think about IoT today, right, it's sometimes just measuring temperature once every 10 minutes or once every half hour. That doesn't require many math cycles. And so really today's microcontrollers are being used for crypto operations, so securing the connection to the cloud. But there's all this other bandwidth that we have to use. So I think that's one big trend that's brought TinyML to the forefront, is the capabilities from a math perspective of the hardware that's hitting the market. On the other end, we have the research community, right? From machine learning, deep learning research has really matured, right? This used to be a really challenging area even in the cloud. And I think the tooling, the algorithms, the knowledge of how to make machine learning smaller and more efficient has improved huge strides, right, in the past 5 years. And that combination, right, of accessible ML technology and then a lot of math capabilities, right, at the microcontroller level is really what came together to make TinyML possible. And the final thing I would say is community, right? We don't build this without a village. And I think what ARM did, coming together with Google, with Qualcomm, and with others to form the TinyML Foundation, right, which really helps promote what we're doing in a neutral way, brings researchers and companies and developers together. I think that's been really key. When that started last spring, gave a big momentum to what we're doing.
Interesting. You talk about that almost professionalization of machine learning, and you see it. You can see it in, say, job descriptions and job offerings, right? What was 4 years ago, companies madly hiring data scientists, right? It was researchers, it was in the cloud, it was algorithm design, but not deployment per se. And now you're starting to see companies, with data engineers, right? Systems engineers deploying the data. It's really going through quite a rapid evolutionary change as things kind of come out of the research lab and start kind of hitting real life, which is fun to see. And I think it'll be the next leg forward in terms of numbers of units deployed and really the business results. Because isn't that what drives everything, right? Is business is actually seeing some sort of meaningful return, on a proof of concept so that it becomes something truly deployable?
That's exactly right. We have job descriptions at Edge Impulse called TinyML Engineer. So it's a new term, but we're actually finding a lot of interest from engineers in the community to go do real production work, right? And that brings us to the latest trend I see happening around TinyML is the move towards ML ops, right? Where we really think about not just experimentation or research, but how can we make developers successful in getting these algorithms to production? We'll talk about that a little bit later, I'm sure, but I think that's an important trend that we start to see.
Thank you for sharing your thoughts here. I can see that the coalescence of several trends has made microcontrollers not just a conduit for implementing IoT applications, but also a powerful independent processing mechanism in its own way. So early this year, ARM expanded its AI portfolio with new machine learning and neural processing IPs, including Cortex-M55 and Ethos U55. U55 is also the industry's first micro NPU. A lot of people see this as ARM's effort to democratize machine learning on low-power IoT devices. So Steve, do you want to talk about this?
Happy to. I think we've seen the explosion interest and growth in machine learning in these tiny little endpoint devices, the sensor devices, the edge. And as companies have learned what they can do with the available horsepower in today's silicon, Obviously we're faced with demands to potentially do more, to put more than just say sound processing, put vision processing in a device, or more than just sensors, but also additional types of sensors combined together to do some sort of fusion and act upon the fused input signals. And that has simply spiked the interest in computational horsepower. So the two new products we did announce earlier this year are both a next generation Cortex-M processor, the M55, which in and of itself takes the machine learning capability of the ARM Cortex-M family to new heights with 15x the performance power for machine learning capabilities. So either the same workload at dramatically lower energy consumption or significant increase in machine learning horsepower within the same energy envelope. And then for systems that need even more performance, we introduced the Ethos U55 micro NPU. That's a companion processor to an M-class core. And that delivers dramatically higher machine learning capability, up to 400x what you could get on existing silicon with existing M-class devices in the field today. And that just opens up the possibilities for what people can do in terms of their analytics on the edge to be able to, I would say, make smarter decisions about what information to send back up to the cloud. So rather than streaming all the information to the cloud, like Zach mentioned, that's too much data in the cloud, is too much to analyze. We can now enable companies to selectively identify events and only flag to their systems when something of interest has happened. When there's both movement and a sound that might, for example, let's say it's a security application and you're monitoring a bunch of buildings on a corporate campus. That a door has moved and you've heard the sound of the door latch, or you've heard the sound of glass breaking or something, right? So you can have an intelligent set of information, not just pumping everything to the cloud, but an actual event has occurred, an anomaly in a production line, an anomaly of a known sort in a building. And that makes it much more selective data to have to work on, to have decision makers or decision-making ML work on that data type. And by pushing that horsepower into those small power-constrained battery-operated devices, it enables a lot more signals in the real world to be processed without having to force feed it all into the wireless network and into the cloud.
Yeah, ARM's new IPs will certainly advance the machine learning and the inference capabilities on billions of low-power embedded devices. I saw a lot of entrepreneurial energy went into the TinyML sector. These new entrances will certainly help drive innovations. So Zach, you also started at Impulse last year. What's the motivation behind this? What problems are you trying to solve?
No, you're right, Wei. Last year has been amazing for innovation in the TinyML space. And we began Edge Impulse really for two reasons, right? As we worked on the first open source project in this space while my team was at ARM, called the Microtensor project. We got some really good experience from working with the developer ecosystem and with partners. And we found that you can solve some really amazing, very low-level problems, right, with some of the compiler technology, I'll call them, which we eventually merged into the TensorFlow Lite micro project. When that project started, we combined efforts. And I really see that kind of low-level tool as a compiler. If you think about the software world, right, compilers are only really small pieces of the bigger stack that we give developers. We give them IDEs, we give them CI/CD testing tools, and much, much more. And you don't actually tend to touch a compiler all that often yourself. We started to see the machine learning world on the edge as being a similar paradigm. It's great that we have a compiler, but to really get developers and successful with TinyML, we need to give them much more. We have to help them collect these data sets with real sensor data. It's really difficult to acquire this data from your devices. We have to organize those data sets and make them useful for machine learning projects. And we have to give access to these algorithms that are appropriate for processing sensor data, processing audio data, or camera images or camera video streams. So making those algorithms available to people in a form that they're already optimized for the types of targets that we're talking about here, right? Microcontrollers or microcontrollers with acceleration. Those algorithms really are out there today. They're very, very hard to find, and they're very, very hard to engineer. So how do we democratize that, make that available to all developers? And then finally, right, I talked about ML ops earlier, right? We think a lot about what does it take to get these things to production? So, live testing, how do you stream sensor data into a test vector, into an ML algorithm while you're still in the cloud? How do you do unit testing? And then finally, how do you handle deploying these algorithms on lots of different targets? So we have to go from, for example, a base Cortex M4 in pure C++ software to, targeting the Ethos U55. That's a very different compiler setup. It's almost completely different. How do you handle that? We also have Cortex M3 parts with DSPs on the side. We have to compile down to DSP calls at times. So handling all those different build pipelines has to be taken care of, because for the user, right, they just need this to work and build a piece of software that can be deployed. So we focused on solving this end-to-end lifecycle problem and doing it with a lot of partnerships. So we partnered very closely with ARM, but also with the ARM ecosystem, the different silicon vendors, Google TensorFlow, data science tools, data set communities. We really have to partner across the entire ecosystem to make this work.
Thank you, Zach. As an embedded engineer myself, Edge Impulse 2 is quickly becoming one of my favorites.
That's great to hear.
Thank you. If you look at the trajectory of TinyML technologies, there has been significant progress in power efficiency enhancement and neural network optimization. So TinyML not only brings new use cases to embedded devices, but also makes a huge impact on mobile devices. We began to see emerge applications in smart home, smart factory, healthcare, and other areas. So Steve, what do you think are some of the most compelling use cases you observed?
Well, some obvious use cases that people instantly think of when they think of machine learning in edge devices or in consumer devices around analysis of image or video. Everything, the phones we all carry around have a tremendous amount of machine learning in them to improve picture qualities, and that's not a tiny device, but a lot of the same techniques are deployed in a lot of the things that are in the home or in the industrial or in the office environment that also use cameras. So image enhancement, whether it be your smart door lock, your smart doorbell, your security camera in a home building or an office building, cameras that look for anomalies in industrial settings, anything having to do with sort of image analysis, image processing, taking an image, finding the region of interest, identifying the object, and identifying whether you have something that is safe or unsafe. Triggering that alarm, whether it be triggering an alert on your cell phone that says someone just dropped off a package on your front door, or triggering a production manager in a factory around something's unusual happening with an expensive piece of machinery that's whirling around at 60 revolutions per second. Whatever the target is, it's a question of quickly analyzing the content and alerting the appropriate decision maker. When someone drops off a package on your front door, you also want to know that a porch pirate isn't coming by 5 minutes later and lifting it and taking it, so you can go to the front door and pick it up. It's even more critical if it's a piece of machinery in an industrial setting where a flaw in the machinery could wind up with severe mechanical damage, or a whole hour's worth of production of contents being lost and wasted due to some sort of error, some sort of misalignment of a device when you're filling bottles or filling packages, etc. So it's a pretty powerful set of capabilities to be able to deploy analysis of signals, analysis of video signals or audio signals or vibration. And then the real question, becomes, well, who or what is making the decision to act upon it? Right? In our home scenario, I mentioned, say, a smart camera on your front door. you're the decision maker. You get an alert on your phone, you can take action. I'll turn to Zach and ask, the tools that you guys are building, you're having to enable businesses, enterprises to make smart decisions on data. Because analyzing data is wonderful. Okay, great. What do you do about it? How do people integrate this? This gets back to your question about ML ops, DevOps, right? Getting smarter, insights still has to get integrated into some sort of decision-making system or some sort of production management system or some sort of, security analysis system. So someone's got to do something with it. Machine learning doesn't replace humans. It just makes us more powerful. And that's the next phase of this, right? The technology's there to analyze these signals, but the decision-making has to be deployed. And that's really, I think, the next phase.
Yeah, and we're seeing the kind of merge of these TinyML algorithms with IoT systems. And that's really where we see that coming together. For example, at Edge Impulse, when we deploy a TinyML inference package, the package does not send the data anywhere on purpose, because our developers might do many different things with the data. They might use it locally for a local decision, or they might send it to one of the cloud systems that they already work with. But we tend to see those systems in place today or already in planning. So what I see happening is that the data that comes from inference will get pushed into the same kinds of IoT systems that we have today. The requirements for bandwidth and the requirements for the amount of connectivity will be a lot less. What I think we will see is changes in connectivity requirements as a result. So a big trend that we're seeing right now is a push towards LPWAN, and not even just LPWAN, satellite. So there's a lot of new satellite players coming. They're deploying some really, really interesting satellite systems where you can access this cheaply from a small communication module on an IoT device. And that's the kind of thing that TinyML enables, right? Because the amount of data you really have to send is so small. Satellite's fine, LPWAN is fine. So I think we are going to shift in the requirements in connectivity. I see some other applications, right? Just working with our end customers, we're seeing some really fascinating things. And the ones that get me super excited are in human health. So we're seeing a lot of work on really advanced wearable devices for monitoring the health of consumers, but also professionals, right? People working in healthcare environments are highly at risk at the moment, as well as in safety critical situations. So working in mining or in heavy industry, how are these people doing? And we're seeing TinyML be used to monitor things like PPG signals. So that's your pulse rate signal through an optical sensor, on precise temperature, on movement. So do we see someone falling down or having like a sharp impact on their body, as well as audio for things like coughing, snoring. You can do a lot of analysis on audio for these kinds of applications. So human health is a really hot area right now for TinyML. And I think it's because they've done so much with sensors already. They're ready for the next thing, right? They're very mature in their thinking about sensors. We see a lot in machine monitoring. So Steve, you mentioned industrial with images, but we're also seeing things like vibration-based machine monitoring, very common. Current, so electrical power consumption-based machine monitoring, as well as audio and images. And I think we're going to start to see some more sensor fusion too, right? When you could combine vibration with audio and images, you can get even more out of the TinyML algorithm that you develop. So, and then finally, something I'll just throw out there that I think is inspiring is TinyML for animal conservation. So we have a customer project that's in progress right now, where we are analyzing thermal images of African elephants out in the field at very low power. So a kind of advanced camera trap where we can really tell at this camera trap, was that an elephant or was that, for example, a goat or a person? And that kind of real-time telemetry is life-saving for elephant conservation in the field. So that's something we have in progress right now on an ARM-based Cortex-M part.
So TinyML broadly encapsulates the field of machine learning technologies capable of performing on-device analytics of sensor data at extremely low power. Between hardware advancements and the TinyML community's innovations in machine learning, it's now possible to run increasingly complex deep learning models directly on microcontrollers. Zach, can you walk us through the future of TinyML as you see it, and pioneers like ARM and Edge Impulse will play in it?
Thank you, Wei. No, I completely agree. It's going to be a fascinating space, and we're just getting started. And so the sky's the limit on where this will go and how we can use it. I do think we are in an early adoption and education phase of TinyML. I think we have to keep that in mind, that it's really important that all of us involved in the ecosystem, we need to be helping people along. So the more we can do to educate people about what is machine learning on an edge device, what does that mean, right? What's the difference between training and developing algorithms, something we usually do in the cloud, we need quite a lot of compute and user experience around it, and then the actual inference, right, that gets deployed on the device. That's something we need to educate people about. It's not obvious how that works. The same goes for the applications of TinyML. Like, what's possible, right? Steve and I have been talking about real-time sensors, audio, images. Are we going to be doing, facial recognition on a Cortex M4 part? No, we're not. That's outside the power and math budget that we have today. Will the micro NPU architecture speed these things up? Absolutely, they will. And so some new things will become possible on these parts. How do we educate people about what the applications are that are appropriate for different size parts? That's something that comes up to us all the time as a question, right? What size part do I need for this application? People don't know. And then I see us seeing the early adopters in the enterprise customers, right? So we see the kind of the most advanced customers starting to really deploy TinyML in real products today. And that's great because we'll start to surface the showcases and use cases from them, right? What's possible, what people are deploying today. And I think that will inspire a lot more people. So many years down the road, I do see us making ML a normal piece of the software stack. This becomes just one module on our embedded software stack that everyone knows and uses in the industry. And I think we will get there in the future together.
Okay, we have to ramp up in a few minutes. Before we ramp up, Steve, let's hear your thoughts of TinyML's future.
Echoing what Zach said, I think what's fascinating, what's happening right now is that we're transitioning from ML being something that needs a data scientist, that needs an algorithm developer, that needs a mathematician. You have to go get yourself, to MIT or Stanford, data science, PhDs in order to do anything, to where you can take existing models that have been developed, that have been proven, and deploy them to, different scenarios. So one good model built by one data scientist can be democratized, productized in 1,000 different deployments. Can use it in 1,000 different industries, or 1,000 different hospitals, or 1,000 different personal care devices, adapting to the specific situation and making it, as Zach said, sort of a building block of an overall application. You can be a data engineer, as we talked earlier, without having to necessarily be a scientist and know all the math inside it. And that's the thing that's going to lead to an explosion of use and explosion of these devices, and really take us forward over the next couple of years. And it's going to be an exciting time to watch.
And something you said there's really important, data-driven, right? I think that's something that we all have to get our heads wrapped around in this space. We're now getting into data-driven algorithms. Let's collect that data and apply that to these algorithms over and over again. And that way we can specialize and personalize these things for customers. And I think that's fascinating, right?
Yeah, I think TinyML represents the collaborative effort between embedded ultra-low power systems and machine learning communities. So this union has opened the floodgate for new and exciting applications on these embedded devices. So Steve, Zach, it's a huge honor to talk to you today. Thank you for sharing your thoughts with us.
Thanks for listening to ARM Presents Fireside Chat. ARM's technology is at the heart of computing and connectivity. Their advanced, energy-efficient processor designs have enabled intelligent computing in more than 150 billion chips. You most probably have ARM tech in your smartphone, and increasingly, it's in the world's most powerful supercomputers. If you enjoyed this podcast, we'd love it if you could leave a 5-star rating and tell a friend. For more information on ARM, visit arm.com.